even powers. Okay. Okay, let's just make a table of values. Now, some of these y values are going to be so huge that I'm not going to plot them. Like, at negative 3, I got negative 3 quantity to the fourth is 81. At negative 2, I got negative 2 to the fourth is 16. I will plot that one. At negative 1, I've got negative 1 to the fourth is 1. At 0, 0 to the fourth is 0. Now, because of symmetry, when I plug in 1 and when I plug in negative 1, I get the same y value. They're mirror images across the y-axis, which we see is true. 1 to the fourth is 1. 2, we got 2 to the fourth, or 16. 3, we got 3 to the fourth, or 81, which, I won't reach that high. But I will go up to 16. And, yeah, up to 16. Okay, so I've got, let me just start at 0 again. I've got 0, 0. I've got 1, 1. And I've got negative 1, 1. Again, mirror images across the y-axis. And then I've got 2 comma way up here at 16 and negative 2 comma way up here at 16. And, I'm not going to plot them, but I'd have 3 comma 81 and negative 3 comma 81. Now, again, if you've never seen this kind of shape before, okay, these 5 points or 7 points or whatever are really not sufficient to see what's going on, okay. I'm going to go ahead and plot this on the calculator to compare some things. Now, notice that, y equals x squared goes through 0, 0, goes through 1, 1, and goes through negative 1, 1. So does y equals x to the fourth. Goes through 0, 0, 1, 1, and negative 1, 1. But what's going on between negative 1 and positive 1 is quite different between these two graphs, and that's what I want to illustrate on the calculator. Let me type in x squared and then x to the fourth. Remember, I have an old-fashioned calculator. That's how mine writes it. Okay, I'm going to start with a zoom 6. Here comes x squared. Here comes x to the fourth. So first of all, one thing you notice as comparing the two graphs, y equals, x to the fourth is a lot skinnier, a lot steeper than y equals x squared, because when you take a number like, negative 2 and raise it to the fourth power, you get 16. You take a number like negative 2 and square it, you only get 4. The y values on this graph are a lot bigger, at least when the x's are bigger, like to the left of negative 1 and to the right of positive 1. The y values are a lot bigger, so the graph of x to the fourth is a lot steeper than the graph of x squared. They do, however, kind of look similar. Now, I want to really zoom in on what's happening between negative 1 and positive 1, because that's where, there's big differences. So I'm going to make my x min just go from -1 to +1. And there's nothing going on below the y-axis, but maybe I'll just go from -1 to +1 on the y-axis, okay? So I'm just looking at this little square, and here this little square, and comparing the two graphs. Now the first one that's going to come up is y equals x squared. And then here comes y equals x to the 4th. Y equals x to the 4th is a lot flatter. This is -1 to +1. On the interval from -1 to +1, okay, the x to the 4th graph is a lot flatter than the graph of y equals x squared. For example, let's say you take x equals 1/2. If you square 1/2, you get 1/4. So when x is 1/2 on x squared, the y value is 1/4. But on y equals x to the 4th, you plug in, wherever it is, y equals x to the 4th, just imagine it. Take 1/2 and raise it to the 4th power, you get 1/16. So the y value is really, really small compared to a y value of 1/4 on y equals x squared. So for any of these fractions between -1 and +1, the y values on y equals x to the 4th are a whole lot smaller than the y values on y equals x squared. So when I'm graphing this function, I kind of emphasize the flatness of it. Okay, so I kind of draw it like that. It's really flat at the origin, near the origin. And then after that, it's really, really steep. Okay, so that's what the graph of f of x equals x to the 4th looks like. I mean, it kind of looks like a parabola, but technically it's not a parabola. There's a definition of a parabola, and this graph doesn't satisfy it, but it's kind of like that, except it's a lot flatter near its vertex. Okay, now let's just look at, here's the values. Let's look at the domain and the range of the function. We can look at the domain from the equation and also from the graph. Range, we'll just look at the graph. So just from the function itself, what's the domain?
Real.
All real numbers. No x's in denominators, no square roots, so no x's under square roots. Domain is all real numbers. And looking at the graph, okay, again, even though this graph is really, really steep and clearly it goes up forever, it goes out to the left forever, again, very, very slowly because it's so steep. And it goes out to the right forever, again, very slowly because it's so steep. But, I can plug in -3 for x, and the y value is up there at +81. I can plug in -5 for x, and whatever that is, -5, what, 625 or something, okay? But, so this graph goes out to the left forever, out to the right forever, even though it's kind of hard to see that. It does. Now, what about the range of the function from the graph? Is the range all real numbers? No. Okay, what's the range? Yeah, just positive y values. When you take a number and raise it to the 4th power, the smallest number you're going to get is 0, okay? You're not going to get any negative numbers. There are no negative numbers in the range, okay? But I'm going to get 0 as a y value, and I'm going to get any old positive number as a y value. So if we want to write the old notation, the set of all y such that y is greater than or equal to 0, or in interval notation, what would it look like? So bracket 0, comma infinity. Okay. Okay, let's graph f of x equal to the absolute value of x, which hopefully you graphed functions, this function and functions like this a bunch of times in Math 60, but again. Any symmetry?
Y-axis?
Yep. Symmetry with respect to the y-axis. If we plug in the opposite of x for x, the absolute value of negative x is the same thing as the absolute value of x. The absolute value of negative 3 is the same thing as the absolute value of 3. Okay, so for any negative number, we take its absolute value. We just get the corresponding positive number. The absolute value of 0 is 0, and the absolute value of any positive number is just that positive number. And again, we can see the symmetry with respect to the y-axis happening. When we plug in -1, when we plug in +1, we get the same y value. When we plug in -2, when we plug in +2, we get the same y value. Same thing with -3 and +3, etc. Okay? Okay. All right, so 1 square, 1 unit. All right, so I've got 0, 0. This is the way I typically plot it in the future. I've got 1, 1. I've got -1, 1. I have 2, 2. I have -2, 2. 3, 3. -3, 3. 4, 4, -4, 4, etc. I have what people call a V shape. Okay, vertex at the origin. So it's composed of 2 portions of lines, 2 rays. What's the slope of this line when x is less than 0? What's the slope of that portion of the graph? What's the slope of that portion of the graph? -1, right? Because it's going down. And the slope of that portion of the graph? +1. Okay? So your basic absolute value function, this one, just f of x equal to the absolute value of x, has a graph which is a V shape. The slope is -1 to the left of 0. The slope is +1 to the right of 0. That'll be important because sometimes we change the slope in certain ways. Okay. Now, what's the domain of the function, either from the function itself or the graph? All real numbers, right? I can plug in any number into the absolute value of x. Again, no x's in denominators, no x's under square roots, okay? And, you know, from the graph here, it is clear that the domain is all real numbers. What about the range? Again, here we need to look at the graph. Positive or 0, right? So y greater than or equal to 0, or bracket 0, comma, infinity. When you take the absolute value of a number, the smallest number you get is 0, you never get a negative number. Okay? Okay, now let's look at f of x equal to the square root of x. Okay. Now, before making a table of values, we should really ask ourselves what the domain is, because I don't want to waste a lot of time plugging in numbers that aren't even in the domain. What's the domain?
0.
Yeah, so here I have a square root, right? So for my domain, I want what's under the square root, which is not complicated this time, it's just x. What's under the square root to be greater than or equal to 0. That's my domain. I don't even have to solve anything. Okay, I can write it in interval notation at some point, but in other words, the only numbers I can plug into this function are 0 and positive numbers. I cannot plug in any negative numbers into this function, or else I get the square root of a negative number, which is not real, and therefore I don't have a real y value. Okay, so in my table of values, I'm only going to plug in 0 and positive x's. Okay, so if x is 0, the square root of 0 is 0. If x is 1, the square root of 1 is 1. Now, okay, I'm plugging in the x's. Why don't I plug in x's that I can find the y values exactly instead of having to get out my calculator and approximate irrational numbers? Like if I plug in 2, y is the square root of 2, but what might be nice to plug in instead of 2 or 3? 4. Because then y is the square root of 4 or 2. What's another nice x value to plug in?
9.
9. Y is the square root of 9 or 3. I could plug in 16 and then get the square root of 16 or 4, but I think we can see what's going on with these points. Okay, so I've got 0, 0. I have 1, 1. I have 4, 2. I have 9, 3. I'd like you to memorize those points. Now, what is the shape of my graph? It looks like half a parabola, and it is half a parabola, because if we compare our y values on y equals x squared, okay, this is my y equals x squared, okay, excluding the ones with negative x values, I have 0, 0, 1, 1, 2, 4, 3, 9, okay, whereas here, I have 0, 0, I have 1, 1, then instead of 2, 4, I have 4, 2. Instead of 3, 9, I have 9, 3. So these points are exactly the same as the ones on y equals x squared, except the x's and the y's have been interchanged. You can't really tell with the 0, 0 and the 1, 1, but here you got 4, 2, 9, 3. Okay, so these points give us a half a parabola, you know, if I exclude the other half there. So this is just a half a parabola on its side. Okay? So we want to know, memorize that that's what the graph looks like. And we want to have these points memorized. These are the nice points where, I plug in 0 and 1 and 4 and 9 because then I can take the square root easily and not have irrational numbers. Okay, now we had the domain of the function just from the function itself. F of x equals the square root of x. But what about the graph of the function? What's the domain of the function from the graph? Okay, so, there's nothing going on to the left of x equals 0. At x equals -1, there's no point on the graph. At x equals -2, there's no point on the graph. For no x's are there points on the graph, because if you try to plug in those x's, you get the square root of a negative number, which is not a real number. So your graph is going to start at x equals 0. Nothing, there are no points on the graph going on to the left of 0. Okay? So, we could say the old way, the set of all x, such that x is greater than 0, like we had here. Or in interval notation, what's the domain?
0.
And bracket, right? Because 0 is included, so bracket, 0, infinity. Okay, now the range of the function, we couldn't tell that from the function itself, the equation. But what about the range from the graph? So are there any negative y values? No. When you take the square root of a number, you never get a negative number. Sometimes you get 0. The square root of 0 is 0. So y equals 0 is in the range. How far does the range go?
Infinity.
Infinity. Again, this keeps going up and up and up forever, slowly. I have to go way out here to 16 to get y equals 4. And then I have to go way out to x equals 25 to get up to y equals 5. But it does keep going up and up and up forever. Okay. So my range is the old way, set of all y, such that y is greater than or equal to 0, or in interval notation, same as the domain, bracket 0, infinity. Okay? Now, it's nice to know that, when you have a square root function, okay, like all those very complicated square root functions we had on our domain sheet last time, that, when you have your domain x greater than or equal to something or less than or equal to something, the graph just starts or stops there. Okay, there's nothing going on, no points, on the graph except the points in that domain. And later I'll look at some more complicated ones like we looked at on our handout, but let's at least graph this one. Okay, so f of x equals 1 over x. Okay. Now, are there any domain issues with this one? Yeah, what do we have to worry about with the domain? Yeah, so we don't want the denominator, there is an x in the denominator, we don't want the denominator to equal 0, okay? And, the only denominator is just x by itself, so in other words, x cannot equal 0. And if I want to write my domain in, set builder notation, the set of all x such that x is not equal to 0. So 0 is the only number that is not in the domain. Okay. Now, so you may or may not have ever graphed a function like this with x's in denominators. You may or may not have ever graphed it by hand, so I want to show you what's going on very carefully. We're going to need a lot of points. Oops. No zero, right? Okay, leave a bunch of space there. Leave a lot of space there. I'm going to put in some fractions in here. And then I'll have my 1 and my 2 and my 3 and my 4, but let's look at these first. Okay. If x is negative 4, y is 1 over negative 4, which is negative 1/4. If x is negative 3, y is 1 over negative 3, which is negative 1/3. When x is negative 2, y is 1 over negative 2, negative 1/2. When x is negative 1, y is, I'll leave myself room, 1 over negative 1, which is negative 1. Okay, leave a bunch of space. When x is 1, y is 1 over 1 or 1. When x is 2, y is 1/2. When x is 3, y is 1/3. When x is 4, y is 1/4, etc. Okay, let me plot those points. I'm going to make this is going to kind of take up the rest of the page. Okay, so I have, just make it square 1 unit. Okay, I'll start with a negative 1 comma negative 1. And then I have negative 2 comma negative 1/2. Negative 3 comma negative 1/3. Negative 4 comma negative 1/4. Negative 5 comma negative 1/5. Negative 6 comma negative 1/6. What's going on here as I keep choosing smaller and smaller x's? What do those y values do? Yeah, they get smaller and smaller. They get closer and closer to 0. So the graph gets closer and closer to the x-axis. Okay? Negative 1/4, negative 1/5, negative 1/6, negative 1/7, negative 1/8. I can't. They're very, very, very small. On the other side, the same thing. Okay? I've got 1, 1, 2, 1/2, 3, 1/3, 4, 1/4, 5, 1/5, 6, 1/6, etc. The larger my x's get, the smaller my y's get. So the closer the graph gets to the x-axis. Okay, that's something important. We'll give you a name for that and some notation and so on and so forth. Now, x equals 0 is the only number that is not in the domain. Okay, all of these fractions, 1/2, 1/4, 1/3, negative 1/2, negative 1/3, negative 1/4, all of those fractions, okay, between negative 1 and positive 1 are in the domain. It's only x equals 0 that is not in the domain. Okay, so let's see what's happening. I think I'll do the positive fractions first. Okay, so what I'm going to do, here we got undefined. But I'm going to pick some numbers really close to 0 on the positive side and on the negative side. Let's plug in 1/2. Okay? When x is 1/2, y is 1 over 1/2. What's 1 divided by 1/2?
2.
2, right? It's 1 over 1 times the reciprocal, 2 over 1, so 2. When, say, x is 1/3, y is 1 over 1/3, which is 3. When x is 1/4, y is 1 over 1/4, which is 4. Okay, so let's look at those points, and then I'll do it on the other side. Okay, so when x is 1/2, y is 2. When x is 1/3, y is 3. When x is 1/4, y is 4. Maybe if x is 1/10, y is 10. If x is 1/100th, y is 100. Okay, so the closer these x values get to 0, the larger the y values get. The closer the x's get to 0, at least on the right-hand side, the larger the y values get. But precisely at x equals 0, there is no point on the graph. There is no y value. Okay? Now, same thing happens on the other side. So say I choose x equals -1/2, -1/3, -1/4. So if x is -1/2, y is 1 over -1/2 is -2. When x is 1/3, I'm sort of out of room, 1 over -1/3 is -3. If x is 1/4, 1 over -1/4, 1 over -1/4 is -4, etc. Okay, so when x is -1/2, y is -2. X is -1/3, y is -3, x is -1/4, y is -4, etc., etc. The closer the x values get to 0 on this side, okay, the smaller the y values get. They get larger and larger, but with negative signs attached to them. Okay, this is what my graph of f of x equals 1 over x looks